Yeah, I will just introduce Aditya maybe. Just a moment, actually, I forgot to, maybe I need to share first. Aditya is a postdoc working at ISC Bangalore, and he has worked on magnetoelectric and multiferroics, as well as spin caloritronics. And he has developed several experimental facilities related to multiferroic spin caloritronics and antiferromagnetic spintronics. And his PhD was in the year 2015, and title was Electric and Magnetic and Magnetocaloritic Studies of Magnetoelectric gadolinium oxides and other compounds. Okay, Aditya, so you can now start your talk. The title of the talk is Probing Magnetic Anisotropy and Spin-Orientation Transition using Spin Hall Magnetoresistance. So let me stop sharing. Okay. Can you go to the full screen?
Sure.
Yes.
Hi.
Okay.
Good afternoon. First of all, I would like to thank Professor Pranab for organizing this conference and giving me opportunity to present our one of the recent works. So the work is titled Probing Magnetic Anisotropy and Spin Reorientation Transition in 3D Antiferromagnet HO DYFO3 PT using spin Hall Magnetoresistance. So this work is the collaborators, and Priyanka Garg is a PhD student who also considerably contributed this work. So I have organized my talk in the following manner. First, I will discuss the motivation and relevance of doing spin transfer studies in 3D antiferromagnets. Then I will give a brief introduction to spin Hall magnetoresistance, and in that I will discuss one phenomenological model to understand SMR in terms of absorption of spin currents at heavy metal magnetic insulator interfaces. Then I will talk about magnetism and spin reorientation transition in 3D antiferromagnets. Then I will also highlight why we are choosing HGA4 PT, this particular material for spin transport. Then at the end, I'll discuss our spin transport results, and then how we understand using a computation of the SMR using a simple model. Yes. So this spin transport at magnetic insulator and heavy metal interface has attracted great attention over the last decade. So like spin-spec effect was observed in 2008. This is the first paper. And the spin-spec effect is basically you apply a thermal gradient across a magnetic insulator, and then you generate a pure magnetic spin current. And then when that spin current reaches the interface, then you can pump that spin current into the heavy metal, and then you can detect as a voltage. So initially, here what I did here is I just fetched some archive preprints from the repository to just get the idea of this cumulative count of different keywords appearing in the title or the abstract. So you can see that from 2008 onwards, spin-spec papers are really increasing in number. However, another discovery, which is a spin Hall magnetoresistance. This one of the first papers in 2013. Here, you're doing something different. You're generating the spin current electrically. You're passing the charge current in the heavy metal like platinum, tantalum, and then you generate a spin current. And that spin current, when it approaches the interface, at that interface, it can get absorbed because the spin transfer torques, and that is quite useful as a probe to the magnetic structures at the interface. So you can see here even SMR also trend is like number of papers every year is increasing. Then there is another interest. Instead of just trying collinear magnets like ferromagnets or ferrimagnets, people started exploring antiferromagnets. And particularly, antiferromagnets can give you much a variety of like spin structures, rich spin structures. So you can see this is one of the first papers, like it's a spin hall Magnetoresistance antiferromagnet normal metal bilayers came around 2017, and then people started not only studying collinear antiferromagnets but also trying to study some exotic ones like spiral magnets and all. So in our group we have been studying such materials in thin film as well as single crystal forms. So okay, let me talk about some recent trends in this antiferromagnetic heavy metal devices. One of the things we can observe that antiferromagnetic passive layers are recently been used in nylon spin walls. The spin walls are having structures like this. You have ferromagnetic insulator, then antiferromagnetic insulator, then you have ferromagnetic insulator again, sandwich here, and you have heavy metal on the top. Similarly, you have like another interesting thing is like trying to manipulate or switch nil vector and antiferromagnets using spin orbit torques generated by the charge currents in the heavy metal. So these are also like the many papers have come in a couple of years talking about in-plane switching of nil vector. And a third important point is that this probing orientation of nil vectors in antiferromagnets using SMR. So SMR has been shown a good potential to even not only to probe the magnetic structures, but even in antiferromagnets, it can really find orientation of nil vector. So that's why it's quite highly used in antiferromagnetic like switching based memories. Lastly here, we want to work on 3D antiferromagnets because peculiarly it can provide two handles for manipulating spin transport with field. For example, like when you apply magnetic field at a sufficiently higher magnetic field, the nil vector tries to go away from the magnetic field, say perpendicular after spin flop. And on the other hand, if you have some net moment, magnetic moment in the system because some slight spin cutting in 3D antiferromagnets, then you can get a net magnetic moment, and then that vector would like to go along the field. So there is a compression in these two vectors, how they will allow go away from the magnetic field. So that gives a kind of a good two handles. So with this motivation, we wanted to work on 3D antiferromagnets. So first, now I'm going to discuss here what is SMR. So just like in semiconductors, we talk about charge transport and we talk about like hole transport and like electron transport. So there we use this drift diffusion equations. So similarly, this paper talks about theory of SMR, where they use quite a classical this approach of understanding the spin transport inside and across this bilayers. So it's a drift diffusion equation. Only difference here is that spin currents are basically tensors. So it is a collection of two vectors. One is a spin polarization, and second is how the spin flows. Now, when you talk about this equation, you can see here mu s is a vector. So here potentials, spin potential is a vector, and you basically try to solve this equation with some boundary conditions. Now you can see here whenever we okay. Now here is the device. Is the top view of the device. Is the side view of the device. So here we have a magnetic insulator, and we have a platinum hall bar on top of it. So what we do, we pass charge current JCX along the x direction in this platinum bar, and then when you pass that, because of the spin hall effect, you can see the term here. The total spin current is a combination of drift spin current and different spin current. So what happens when you apply charge current? Because of spin hall effect, you have a spin up and spin down electrons. They like get separated out and they go move in opposite direction. That's why you get a spin drift current given by this theta sh is a spin hall angle. And then once spin starts accumulating at the interface of platinum, then you will always have spin diffusion current following in the opposite direction. So if both the interface, top interface and this interface of platinum are like perfectly reflecting, means no current spin current is lost there, then we can say that no spin current is lost at the interface, and it is a perfect reflecting boundary condition. And then you will have spin-off effect and spin acceleration this way. And okay, now, but if you are having the magnetization beneath, which makes the angle other than so if it is not parallel to the M, suppose M and mu s, they are not parallel, then what you have is, because of spin transfer torque, you have this term and you get a some current which gets absorbed at this interface. So when you solve this equation, then you have to use one boundary which is reflecting and one boundary is absorbing because spin transfer torque, and that gives when you solve it, you can see here the spin accumulation is different from the previous case. So what happens here? Since there is spin transfer torque between magnetization beneath and the mu s spin polarization, since magnetization is like a pin with magnetic field, then the torque basically rotates back the mu s in the bulk of the platinum. And this balance, where the both currents were net current was zero earlier, now the net current is not zero; it's a finite, and that net spin current gives rise to charge current because of the inverse spin effect, and that can basically change the resistance or resistivity of the platinum layer. So you can see here in this scenario, the SMR, like a resistance of platinum, is changed, is higher than the equilibrium value, and when you, so this simulation shows that as you rotate the magnetic field, your spin accumulation in the platinum mu s is changing in the bulk, and that changes basically modulates the resistance of the platinum. There is a longitudinal resistance rho xx, and there is a rho xy transverse one. So in our studies, we are going to mainly show this transverse resistivity measurements. Only one point to be noted here is that here we can see that when we rotate the H in plane, the aim is following that. It means that we are assuming here is a ferromagnetic material, and magnetic field is much above the anisotropy. So aim can follow H. But if you work with the antiferromagnets, then what may happen is that if the Néel vector basically goes perpendicular to H, then this whole signal gets shifted by 90 degrees, and we call that SMR to be negative SMR. So with this introduction, I'll just talk about orthoferrites. So here we are going to work on this DY-FeO3 system. So this is a distorted perovskite structure where you have A, B, and C lattice parameters, and you can see here that rare earth is sitting at these positions, and Fe atoms are at these positions, and S1, S2, S3, S4 are Fe spin moments, and they are situated at these atomic positions. Now, for a particular case of this HODY-FeO3, we are using single crystal for studies, and ABC lattice parameters are these. Now, in order to understand spin configuration in the system, we can always write a simple model Hamiltonian, where you can see that the magnetism become complex just because you have various like superposition as well as DM interactions. For example, first three terms are superposition interactions. You can see like JC is basically out of plane interaction within the spin moments. JAB is in this plane, and JNN is the next neighbor interaction. So all three needs to be considered in these three antiferromagnets. Next is the DM interactions. So in this figure, you can see that these vectors are shown here with the green arrows, and you can see that the D34 and D12 interactions are in plane because there is no Z component here, and D14 and D23 are being slightly out of plane. Now, so DM and this both all the interactions terms like helps you which actually results in counting of the like moments as well, which I'll show now. Another thing important thing here is anisotropy energy terms. So in order to understand what people do here is that all these spin moments of Fe sublattice S1, S2, S3, S4, they define the basis vectors like F, G, C, and A. So you can see here F is just a addition of this all moments, the net moment, whereas this G, C, A are, if you see this negative signs, they are like Néel vectors, three different Néel vectors. And what you do is that once you have some spin configuration which in this material, basically that is just a linear combination of this 4 basis vector. So now you see that like since there's a PBNM structure, so for that specific PBNM, you can have various representations, and they can be shown in the Berthoud notations: gamma 1, gamma 2, gamma 3, and gamma 4. And our concern in this study is gamma 4 and gamma 2 phases. So gamma 4 phase, if you see, it is like defined as the G is along X, A nil vector is along Y, and F net moment basis vector is along Z. So these three, that's how we can identify the phase. Fine. So with this, so this is the here's a single crystal of HO-DY. Why we chose this? Because at room temperature it shows gamma 4 magnetic phase, and at low temperature it will show very low temperature below 25 Kelvin, it goes to gamma 2 phase. And there is a little bit like a complex phase transition, first order, between gamma 1 to gamma 2 first. Sorry, gamma 4 to gamma 1, and then there is some region gamma 1 2, and then gamma 2. So so we did magnetization measurements at room temperature, and we can see here when you do measurement along C-axis, you get this like sharp square hysteresis loop. So here the coercive field is around 713 oersted we found, and this switching why is happening? Because in gamma 4 phase, if you see in a previous slide, we are talking about GX, AY, and FZ thing, and here we see that we have like two possible degenerate spin configurations. One is gamma 4 GX FZ, and other one is gamma 4 minus GX minus FZ. So basically, the spin configuration is kind of like flipped along plus C and minus C direction. So this switching is basically between these two spin configurations. So what we do in our study, we are interested in understanding this magnetic anisotropy, and we try to do measurements with fields less and above this critical field. So our experimental setup is a bit simpler here. It's a homemade setup. So what we do is that this is the HJ4 single crystal. On that you have this platinum hall bar, and then what we do, we pass charge current in this direction, say AC RMS current 1 milliamp, and then we measure transverse voltage in this case, and we rotate the magnetic field in plane. So here either we can rotate the magnetic field, or sometimes we keep the field constant and rotate the sample. So we do both ways, setups. So I discuss the results here now. So first we are looking at the very high field, at high fields, what happens with the SMR. So this is the raw data. When we measure the transverse resistivity as a function of alpha angle when you rotate the magnetic field, and this is shown at 3000 oersted to highest field is 16 kilo oersted. And one peculiar thing we see here that when we saw earlier in the simple ferromagnetic systems, we saw that SMR is quite smooth and it has a kind of sine to theta behavior. But here, first observation is that raw data doesn't have 180-degree periodicity, and there is some asymmetry here, which is marked by these arrows. Then we realize that so there is a sharp change, very sharp change happening in the SMR. So that may be like indicative of some anisotropy, competition between Zeeman energy and anisotropy. So what we do here we correct this data basically. So what we realize here is that since we are doing transverse SMR measurement, you know that if you though we are rotating magnetic field in plane, but if the sample is a bit tilted, then there will be some out of plane field component. And when you rotate a sample, there will be a wobble in the sample, and you will have a sinusoidal out of plane component, and that will give you ordinary Hall effect creeping in your SMR measurement. So we had to take that out. Then only we got symmetric 180-degree periodic SMR, which is plotted here. And then amplitude of this kind of artifact or unwanted contribution, amplitude of that is A, ordinary Hall effect. That we are plotting as a function of H, which is quite linear as expected. That's why we are removing that. And the remaining part is the SMR amplitude that we are plotting as a function of H, which is showing some nonlinearity here. Now one more observation here, that around 90, you start at 0 degrees, you are along the C-axis, magnetic field on C-axis. When you cross the axis, after 90 degrees, sudden change happens here, and there even the sign of the signal also changes. reverses. So basically the whole signal is we call negative SMR here. Now in order to understand this, what we're doing, we're trying to now compute SMR. So earlier, one of the slides, I showed that there's a simple model Hamilton we're using. So what we do is that we try to find the equilibrium spin configuration by minimizing this energy. And to do that, we have used, in this table, we have mentioned all the numbers which we used. We borrowed some reference numbers from like parent systems, like RFUD systems, and we have to bit change it. And these numbers are, with this we are able to find out what is the equilibrium spin configuration. And once you find that, then your transfer signal is basically, it has three parts. Like first is your SMR. So once you know spin configuration, then you can plug in these values of SI, X. So basically, it's a X component of your spin moments, and then this will give you SMR. And you know that the other thing we already taken out, Hall contribution, and we, with the simulation and our experiment, we realized that there is no anomalous Hall effect. There is no out of plane spin moment in the system. So these results when you're plotting here, So it is shown at, say, okay, what we did here when you're doing simulation, since model is simple, so we are using normalized like field H by HC and doing the simulation, because HC is 713 hosted, and we just want to focus on doing the simulation or understand results just below and above the HC. That's why this approach is quite working here. And then you can see we are able to reproduce the SMR behavior with the hysteresis. And then to get more insights into it, what we're doing, the spin configuration, what you have minimized, we're trying to find out what are the basis vector, like F, G, and thing, A. And then we are just plotting here basis vector components. And you can see here, so FZ and GX, these two, this sharply changed around 90 degrees, whereas other components, GZ and FX, they change very smoothly. This on the simulation. So to get more insights and idea, if you look at this schematic, what's happening here? It's a little exaggerated schematic. When your field is along Z direction, alpha is 0, what happens? You have this F spins are like they're canted towards Z axis, and you have a net moment F vector along Z, and the G vector, which is the next prominent antiferromagnetic vector along the X direction. There's a gamma for phase in one domain. Now we are above the HC field and we are rotating it. Then you can see that when you rotate the magnetic field, this configuration rotates, but doesn't follow really the magnetic field. It lags, and when it goes above 90 degrees, it suddenly switches to other direction. So this angle is exaggerated. So that's why you are getting this thing. So it's basically we are seeing here compression between Zima energy and your anisotropy energy, probe with spin-Hall magnetoresistance. Moving forward here. So now we are doing two specific measurements. One, when we apply magnetic field, external field, greater than your critical field, which is 713 hosted, required to do the switching between the two domains. And you can see here that these measurements are shown from 800 hosted to 3 kilo hosted, because we know that 713 hosted is the critical field. And we can see that we have very broad hysteresis in the measurements. And then as you increase the field, then we can see there's a decrease in the hysteretic region. So it also clearly indicates that your Zima energy at high field is now kind of like competing and dominating your anisotropy energy. And now, and also we could do simulations, and you can see they're fairly able to reproduce our experimental data. So same observation that when you're above HC, the periodicity of the signal is 180 degrees, and but behavior surely deviates from conventional sin to alpha behavior for your collinear ferromagnets. It has such sharp features. And other thing is that yes, so our simulations also they are like able to understand, able to match with the experiments. Now, other scenarios interesting. When we apply magnetic field below HC, so you don't have enough field to do the switching between the two domains. So, so to do this experiment, what we do is that we apply first the magnetic field of say 2 kilostate above HC, field above HC, along say Z direction or C direction of the crystal, and then we get a single domain, and then we remove that field, and then once you remove the field, you know that there is a remanence, so the domain stays, and then we apply field less than the HC, and then we rotate the magnetic field. So since the field is less than the critical field, it cannot really switch the domain. So we have a single domain. One of these domain we prepare first, and we do the measurement. So you can see here quite interestingly that SMR signal has a periodicity of 360 degrees now. Because conventionally it will be 180 degrees, but since the domain is like pinned in some way, and it only little oscillates around this equilibrium position when you rotate the magnetic field. That's the reason for this. So then we also try to do simulation at those low fields, and we could confirm that whatever this mechanism we're expecting, which is working here. So one of the uses of this such 360 degree periodic signal is that you can see that a signal here and here, it's exactly opposite. So if you want to make some magnetic sensors, where you want to know the magnetic field direction, up or down, whatever, then this such SMR measurements on such domains can be helpful. Okay, and now I'm coming to the last part of our studies in this study. So we are doing SMR measurements at low temperatures to understand the spin reorientation in the system. So, so you can see here, to do this measurement, we used say constant field of say 2.4 kilostate, and then that magnitude of H external we rotated in the AC plane, and we did these measurements at various constant temperatures, say from room temperature to down to 11 Kelvin in the lab. And you can see here that 300 Kelvin, we saw that data was like this, and it had some hysteresis. It's only one of the scans shown here. But as you go to lower and low temperature, down to say 150, we can see that hysteresis is decreasing. Second thing we observe is that from say 125 Kelvin down to 45 Kelvin, because the gamma 4 phase persists down to 49 Kelvin. So we are still in the gamma 4 phase. We can see that there are a few more features are like evolving. So basically skewness of the data is decreasing, and it became much more roundish and kind of approaching towards the collinear ferromagnets SMR. So with this, what we argue is that as you lower the temperature, hysteresis decreases, and these features, the way they're evolving in gamma 4 phase, they point towards basically the weakening of anisotropy and down to in this region. And then when you decrease the temperature further down, then we saw that earlier that there's a complex mixed phases of gamma 1 and gamma 1 2, and then below 25 we get a like a converted gamma 2 phase at low temperature. So when you go less than 25 Kelvin, we saw that the SMR, you can see here it's shifted now. This sharp change here it doesn't happen at 90 degrees now. It happens at 0 and 180 degrees. It means that the hard axis in some way is now shifted by 90 degrees. Because gamma 2 phase and gamma 4 phase, the only difference between the two phases is that the easier hard axis, they are shifted by 90 degrees. So if you compare the high and low temperature phases, we can see that SMR is able to probe even the anisotropy and identify these two phases, gamma 4 and gamma 2. The last part here, when you're like plotting the SMR amplitude from all these measurements as a function of temperature, then we saw that in the gamma 4 phase, as we decrease the temperature, then SMR is increasing initially, and below 100 Kelvin, it's decreasing. So I'm not showing simulations here, but when we did so far, I showed the simulations with only Fe sublattice we are using. But what happens here is that the rare earth also gets parametrically aligned at high temperature, gets aligned, and we saw that contribution was coming even at room temperature. That's why we added that parametric contribution. But as you decrease the temperature, parametric contribution increases, but the parametric contribution is giving positive SMR, opposite side of the SMR what we're getting from the Fe sublattice. So net SMR amplitude is basically decreasing when you add them. So, but that effect gets pronounced only at low temperature when paramagnetism really starts dominating. So this downturn here we argue that that may be coming from like a paramedic contribution that increases. Now, another point is that when you talk about 3D antiferromagnets, you have rare sublattice and Fe sublattice, and you always have the complex interplay between this 4F and 3D magnetism. And also one thing which matters here is the antiferromagnetic coupling between Fe and Re sublattice. So there are some reports show that low temperature even you can have a antiferromagnetic coupling between the Fe and Re. So that's why the low temperature thing we don't have enough magnetic measurements, and this phase diagram is yet to be explored. So we are not making any more comments at very low temperature magnetism here. So with this, I summarize results on this system. So SMR is found to be an effective tool to probe magnetic anisotropy as well as spin reorientation transition in the 3D antiferromagnet HO-FeO3. There's a half substitution here. And our computational results are also in good agreement with the experimental data. And last thing is that the Spintronics studies also highlight the potential of this HO-FeO3 material for future antiferromagnetic spintronic devices, because we saw that we have a net F vector also and nil vector also. So particularly we feel that it has quite good potential for non-local magnetic transport measurements, or even as a combination of passive layers in other spin walls. So fine, with this, I just, okay, this is me. I just thank all the collaborators. All the work is done in-house. So the Priya, a PhD student who worked considerably on this topic along with us, and this Tirthankar Chakraborty, who grew the single crystals with optical flow zone, and that was useful for us. Yeah. So okay, thank you. I end my talk here.
Okay, thank you, Aditya, for this very interesting talk. So